Right, I'll record my lesson. Okay, so last Friday we end off at this point of time. So we say that we were actually discussing what could have affected the number of ligands that can surround our TN cation. So I mentioned that the size matters. So if your ligand is of a bigger size, then your coordination number will drop because a very big size giant around your center, right? These big sizes will have a repulsion, experience repulsion between each other. So there will be less ligands around your cation. Okay, so if your cation size is larger, then there's more space to accommodate more ligands. Okay, so it's this kind of relationship. Then I believe that when I go through inorganic QA review, right, I've emphasized to you that generally the number of ligands will be twice the charge of your cation. That's a general rule. But chemistry is always like that. There's always an exception. Okay, so first thing first I want to highlight is if water happens to be your ligand, then most often it's 6, unless suggested otherwise by the question. Okay, so if the question did not say anything, right, if your water is the ligand, by default 6. Okay, then if it's other ligands twice the charge, then there's always exception. For example, Al3+, iron 2+. Okay, then this one, this is new to you, but this is actually in your data booklet. Right, so if you look at your data booklet, you see other forms of complexes. Yeah. So sometimes you can get some hints from your data booklet if you know where to look for them. If you don't know where to look, you have no idea, then just lose the mark. It's okay. Because there's no way you can memorize everything. All right. So to score A doesn't mean that you have to memorize everything to perfection or every topic to perfection. Okay, we are not asking you to do that. Okay. All right. So let's look at our checkpoint 3. Zinc 2+ and ammonia. Okay. So what will be the coordination number? Based on the rule, that will be 4, twice the charge. So ammonia will be four of them surrounding your zinc 2+. And please take note, ammonia is electrically neutral without charge. Okay, so without charge, so the net charge carried by your complex will be from your zinc 2+ only. So as a result, this is what it will look like. So remember, everything that is inside the square bracket are your cation and your ligands. Anything outside the square bracket are your counter ions. I'm going through the answer to checkpoint 3. Then you miss out on checkpoint 3. Can you follow in pace first? Yeah. Okay, so how about the next part? What will your answer be like? Okay, so you're having water as a ligand. So water as a ligand, same thing, is electrically neutral, so it will not contribute towards the charge. So the net charge will be from your aluminium center. Okay, so water as ligand coordination number by default is 6. All right, so this is what you will get in your complex. Okay, all right, now try to be on par with me. All right, don't do something else during the lesson. Yeah, because okay, so let's look at this part. Part C, okay, this is what you should have learned from an inorganic QA. Okay, if you can remember, you remember lah. So it will be the coordination number 4. Okay, then with 4 of the OH minus and 1 of the 3+, the net charge will be just 1 minus. Okay, I think when I go through this review, I go through it quite fast. Okay, when I go through the inorganic QA. Yeah, so this one will be a revisit lah. Okay, so let's move on. So silver plus cyanide, what will be the coordination number? Yeah, twice the charge. So it will be 2. Okay, so 2 of minus, 1 of plus. So the net charge is a net minus. Okay, So remember the square bracket. The square bracket is very important because the square bracket identifies the cation and the ligands. Okay, and the net charge will be placed outside. So if you look at iron 2 and cyanide, okay, this one is the exception. It's coordination number 6. 6 minus and 1 of 2 plus, net charge of 4 minus. Okay, F and G, you are not required to memorize. If the A-level question requires you to deduce the formula of the complex, they will give you some data for you to deduce what is the mole ratio. Yeah, if you have looked at your tutorial questions, there's one example over there. All right, so this is more complicated in the sense that it's not really in your syllabus, but it can be given to you as one of the applied example. Okay, so in both cases, coordination number 6. So because it's a bidentate, right, this will mean that you need 3 of these C2O42 minus to fulfill the coordination number 6. Then EDTA is already a hexadentate, so you just need 1 mole. So 3 of minus 2 and 1 of plus 3, right? Therefore, a net charge of 3 minus. Then again? No, okay. So for bidentate and hexadentate, right, it will be implied by the question. Yeah, now when I say exceptions, if you can remember, you remember. Cannot remember, then just be kind to yourself. Yeah. Okay. So EDTA, so hexadentate, only 1 mole. So it's 1 of 4 minus, 1 of plus 3. So a net charge of 1 minus. Okay, so this is how it will look like. Okay, so very quickly, right, the rest will be just as such. Okay, so the rest will follow the general rule of twice the charge for non-water ligands. Okay, water ligand by default is 6 water. Can? Okay, any other question about this part? Hmm? What do you mean? In this case, we just follow the rule of twice the charge. Yeah, and also except for Al3 plus, Al3 plus and IN2. Yeah. Okay, Ken? I mean, if you can remember, you remember lah. Okay, so the next part, which is on page 10, systematic name of complexes, do not worry. It's not within the A-level assessment that they ask you for the naming system. You must know how to name an organic molecule. Alcohol, you must know how to name. Alkane, alkene. Okay, not for benzene. Yeah, all right. But for this one, right, no need. Okay, so if they give the name, most probably they will give you the formula of the complex as well. Okay, so there's no need for you to learn how to name this. So this one is for your own interest. Okay, so do not be anxious about this part. Okay, work example number 1. Okay, please take note. Please take note. For copper tetraamine complex, right? Because one of you just asked me, ammonia is 4, so is copper 2 the only one with the 4? I mean, if you follow the general guideline, it's true lah. But then in A-level context, right? Please take note. In A-level question, they tend to represent copper tetraamine in this form. So this is the typical A-level format in an assessment question. They don't show it this way. They show it with 2 molecules of water ligand. Yeah. Cu2 plus. Okay, so please take note, Cu2 plus is a very important TM cation metal because anything related to it, right, you must know in depth. Just like in electrolysis, you need to know how to purify copper. Yeah, so anything related to copper, you must know in depth. Know how to calculate, know how to purify copper, and what are the different complexes related to copper too. Okay, and what kind of reactions does it undergo? All right, so anything related to copper, you should know copper very well. Okay, so qualitative analysis of cation and complex. This one is your inorganic QA. I leave it to you to self-read. Okay, I will not go through review. So page 11, self-read. Okay, it's all learned under inorganic QA. So let's look at page 12 now. So page 12, all right. In relation to transition metal chemistry, you need to know how to identify the different types of reactions that it can take part in. All right. So there are 2 kinds of reaction that TM can take part in, and it will result in color change. Okay. So let's look at the first bullet, success criteria. So I can explain how ligand exchange leads to different colors observed, and particularly for copper-2 ions with water, ammonia, and chloride as ligands. Can? All right. So there are 2 types of reaction that TM can undergo, which will result in color change. So if the question say, oh, there's a color change upon addition of A, then you must be able to distinguish whether it's a redox reaction or a ligand exchange. Okay, and especially for copper-2. And I hope you can recognize that water, ammonia, and chloride are the most often used ligands in TM. Okay, so when I add water, when I add ammonia or chloride ions, you must recognize that it's more likely to be a ligand exchange. Ligand exchange than a redox reaction. Okay? Okay, I'm saying that there's only 2 types of reaction that can result in color change. Okay, so when the question says that there's a color change, it's either redox or ligand exchange. Okay, so if you look at most often used example of ligands, that they will be water, ammonia, and chloride. So if I add either one of these, right, then it's more likely to be a ligand exchange rather than redox reaction. Okay, so you must be able to tell what is more likely to take place here. Okay, then the next bullet one is the carbon monoxide poisoning. So some of you take bio, right? So this one will be like more relevant to you. But I will not go through this. It's in the syllabus, but it's quite a similar concept. So I will not go through this review. This one will be under self-read. Okay, so in relation to ligand exchange, okay, so for inorganic chemistry, please take note, you must know how to write equations for inorganic chemistry, especially. Okay, so after being able to identify the type of reaction, you must know how to write an equation. Okay, so an equation that represents ligand exchange will be through the use of a reversible arrow. Okay, and in an aqua complex, this is called aqua complex because of the water ligand. Okay, remember, this is a reversible displacement. Okay, not a full arrow. So of course, then you will be subjected to LCP, or you can apply LCP here. So for copper-2 complexes with water, ammonia, and chloride as ligands, so you must recognize that the complex formula is 6 water molecules, which is more often known as copper-2 plus equals Now, depends on the question. If the question asks you for the formula of the complex ion, then this is the answer. If you gave this as the answer, you'll be marked wrong. Okay, so you have to read the question very carefully. What does the question want? If the question is asking for formula of the complex, this is the one. Okay. Right. So in the presence of excess ammonia, what will happen is also a ligand exchange. The ammonia introduced can displace the water molecule. So if you follow the A-level assessment, this is how they tend to represent their tetraamine copper 2 complex. So if you write this, right, then instead of having 6 water molecules released, there are 4 instead. Okay, so just make sure that the water on both sides are balanced. So this will give you a deep blue coloration, the tetraamine complex. Pardon again? Yeah, so if you are using this as a formula, then there will be 4 water molecule released. Yeah. So which formula you should use, right, can be suggested by the question. So you have to read the question very carefully. What? 2 or what? 2 plus. Still a 2 plus because ammonia and water is electrically neutral, no charge. 2 plus. Water, ammonia, no charge. So the 2 plus is coming from your copper 2. Yep. All of them are ammonia and water monodentate. If your water is the ligand, it's 6. Yeah. Okay, so in the presence of a high concentration of chloride, then you also have a ligand displacement. So there will be 4 going in, and it's actually yellow in color. Now you have to memorize the color because the A-level question requires you to describe the observation. Okay, so you need to know the color. Okay, and this is how the complex will look like. Okay, so you can copy this. Right, so if you were asked to show the 3-dimensional shape, okay, do recognize that with respect to the ammonia ligand, it's a square planar shape. With respect to the nitrogen, it's a square planar shape. Then if you are having chloride as a ligand, it's tetrahedral shape. Yes. Anything related to copper 2, you must know in depth. Is this copper 2? Yes. Okay, again, if you can remember, you remember, right? If it's too much, then never mind. Okay, so notice that the net charge is different. This one has a net charge of 2 plus because the ligands are all neutral, while this one has a net charge of 2 minus because the ligands carry minus charge. Okay, all right. So the diagram you gave also slightly different depending on what the question wants. If the question wants you to show a 3-dimensional shape, then it will be like this, tetrahedral shape, 3-dimensional. If the question is asking for how bonds are being formed between the ligand and your copper 2, then this is how you draw it. Yeah. Okay. So appreciate that there's a different diagram to fit the different assessment. This one is in your notebook already. Yeah. All right. So you can refer to that. So some of you may ask, how come when the ligands are ammonia and water is 6 of them, while when I change the ligands to chloride, it becomes 4. How come? Why? Yeah, size of the ligand. So what can you say about the size of the ligand? Yeah, chloride is bigger. Okay, how do you know chloride is bigger? How you tell? From your physical periodicity. What do you learn from physical periodicity? Number of inner shell, or rather look at the period. So nitrogen and oxygen are from period 2, while chlorine or chloride, they are from period 3. Okay, so period 3 element has more inner shell electrons, so the size is larger. So larger size means that it can accommodate less around the same cation center. Okay, and you must know how to answer this. Is asked in 2022. I mean, if you can remember lah. Can? Okay, so far so good. Okay, so let's move on. So ligand exchange, copper 2, this one you can read on your own. Okay, notice that we give a lot of equations, so you must know whenever you are writing ligand exchange or ligand exchange, it's a reversible arrow. So this one are your sparingly soluble salt, also are your KSP. So all of them are reversible. This is a weak base, that's why it's reversible. So all the reversible arrow represents different types of reaction, and they have their own reason for being reversible. Okay? Okay, this one you can read on your own, blah, blah, blah. Okay. Yeah, so can I pinpoint to you this particular work example number 3? When you are adding concentrated sulfuric acid, there's no color change. Okay, so like what I said earlier, whenever there's a color change, two likely reason: ligand exchange or redox reaction. When there's no color change, it means that there's no reaction, right? No ligand exchange. Okay, then I would like you to take a look at last year's question, 2023 paper 3, question 3. Okay, so notice that A level like to put water inside, even though it's not really taking part in the reaction. Okay, so in this copper 2 hydroxide, right, we always write it as this. You can continue to write it like this, all right? But in A level assessment, right, when it comes to TM, they like to put water inside as well. Okay, I think they are trying to make it consistent that when your ligand is small, like oxygen or nitrogen, it's always 6. They are trying to make it consistent in their own way. Okay, right? So in this copper 2 hydroxide, which is a sparingly soluble solid, it will react with the following reagent: dilute sulfuric acid, excess aqueous ammonia, and concentrated hydrochloric acid. So that's why these two examples here related to copper 2, you must know them very well. If not, you will not be able to answer this question. Okay, so what do you think will happen when you add acid to your copper hydroxide? What do you think will happen? What do you think will be the type of reaction? And what will be the observation? Yeah. What do you think will be the reaction here? And what will be the observation? Anyone? No one wants to say anything. Huh? Yes, it's an acid base. So you have your H plus coming from your sulfuric acid, neutralizing the hydroxide from your copper 2 hydroxide. So if you were to write an equation, it will look something like this. And please take note, because they use this formula, you must also use this formula. Okay, then you have your sulfuric acid. This is an acid-base reaction. So what are the products formed? Are you able to write? And some of you are very poor in writing equations. You don't even know what's the charge of your cation. Very well. Okay. So in this case, you should know that it's a copper sulfate plus what? 6H2O. 2 moles of water produced from acid-base reaction, 4 moles coming from the original solid. Yeah. So this will be a complete equation. This is the equation that we are talking about. Then what will be the observation? Please take note. This is not a blue PPT. If your idea here is a blue PPT dissolving to form a blue solution, wrong. It's a blue solid. You only describe PPT when it's 2 solutions added together and you have solid form. That is called PPT, precipitation process. But this is already there. All right. So it should be a blue solid dissolving to give what? To give what? Blue solution, not copper sulfate solution. Giving me the formula of the product is not giving me the observation. All right. So it's a blue solution, not copper sulfate solution. This is observation. Okay, so acid-base reaction. Can? All right. So when you look at the second bullet, what do you think is happening over here? Based on the word example that you have seen, what do you think can be happening here? Or based on what I tell you, water, ammonia, chloride, they are all potential ligands. Yeah, so this is likely a ligand exchange. So writing an equation to represent that ligand exchange. Copper, H2O for OH2 plus 4 ammonia. And if it's a ligand exchange, reversible arrow, remember? Then you have your 4 ammonia going in. Okay, then your 2 plus. Okay, okay, so it depends on how you want to do it. So this one will be a 2 plus followed by your OH minus. 2 water release plus 2 OH minus. Okay, ligand exchange. So it will be a blue PPT dissolving to form a dark blue solution. Okay. Again, sorry. The first reaction is acid-base reaction, then copper sulfate is not dark blue. The dark blue is only associated with the tetraamine complex. This one is a blue PPT, blue solid, and this one is the dark blue solution. Blue solid, blue solid. Not PPT, blue solid. I'm not saying PPT. I did not say PPT. I mean, I say blue solid. Yeah. Okay. Then how about the last bullet? What do you think will happen? The last bullet is the most complicated one. What do you think will happen? Because there's H plus, there's also Cl minus. So what do you think will happen? And what do you think will happen first? Yes. So the H plus will undergo acid base first. Then the chloride will undergo a ligand exchange with the aqua complex. Yeah, it's a series of 2 reactions. And yeah. No lah. I mean, if you look at organic reaction, acid base always takes priority over any other possible reactions. Yeah, so you will see the blue solid dissolving first, then it will slowly form the yellow solution. Because yellow solution is your copper tetrachlorocuprate. Okay, tetrachloro complex. Yeah. Okay. Do you know how to write the equation? You should know it. Because acid base is represented by sulfuric acid. You just need to change it to hydrochloric acid. Then ligand exchange, you just need to have, because after it's dissolved, right? The ligand is aqua complex. Huh? Oh, because you want to push the formation of the tetrachloro complex. Okay, notice that it's always high concentration of chloride. Okay, here, in this work example, you need high concentration to push the equilibrium forward to favor the formation of the tetrachloro complex. Yeah, so you can put this as your ligand exchange. Huh? Yeah, when it's dissolved, it will form the aqua complex. CuSO4 is a solution, it's an aqueous solution. If you want to show the ligand exchange, you have to show the aqua complex one. If you write it as this 2+, how do you show the ligand exchange? Cannot, right? Even though these two mean the same thing, but you must write this in order to show the ligand exchange. Yeah, so it's complicated in that sense lah. Oh. Yeah, this one. Okay, so if I write my acid-base reaction first, right, it will look something like this. So my HCl, 2 moles of HCl, correct? Then it will give you the copper 2 plus aqueous plus 2 chloride aqueous, which is the same as copper chloride aqueous. Do you know that they are the same? Okay, then of course you have your 6 water molecules released. That is the acid-base reaction with your hydrochloric acid. Then, after which you follow by ligand exchange. To show ligand exchange, you cannot show copper to aqueous. It must be the aqua complex. Then you show the equation, which is in your work example, this one. Can make sense? You don't just copy. You must understand what's going on. Yeah. Any question? Huh? Huh? Acid-base reaction, there's a salt. This is a salt. Copper 2 chloride is a salt. Just like when you react it with sulfuric acid, the salt form is copper sulfate. I separate so that you can see that copper 2 is later on going to undergo ligand exchange with the chloride. Yeah, it's fine. No, I'm just trying to identify it for you in case some of you cannot see. Yeah. Because I see a lot of question mark on your face. Yes? Full dissociation. Because it's fully soluble. Once it's aqueous, it's already the aqua complex. It's like spontaneous. Yeah. Can? Part two is your chemical periodicity also. Yep. Okay, I will not go through that. Okay. So let's look at page 14. Please read yourself. Okay, page 15. I mean, some of you do physics, right? I think, do you know that why is this table white? Why is this green? Why are your bags black, laptop black? Do you know why? Huh? No, I mean scientifically, why does it appear your hair is black? Huh? Huh? This table appears white because white light shines on it, everything is reflected back, right? That's why it appears white. Your shirt is white. Yeah? So if it's black, it means that light shines on it, all wavelength absorbed. Then if it's transparent, your glass is transparent, right? So if it's transparent, what does it mean? A light goes through and it goes behind the glass, then whatever that appears behind your glass will be reflecting the rays back to your eye, right? That's what is happening. So the color of the complexes you see, observe of TM will be always a color complementary to what is being absorbed. Okay, so can you help me highlight this? And when I say complementary, is most often generally the opposite wavelength. If you look at this color wheel, are you supposed to learn color wheel for physics? Geography? Huh? Geography, I thought you got colors one. Hmm? Huh? Okay, anyways. Yeah, okay. Oh, so you need help also in geography, is it? Oh. Yeah, so in this case, right, if let's say the complex absorb violet, then what is reflected back to you is likely to be yellow lah. So this is what we are trying to say. Okay, and I hope you know that blue has the highest frequency while red has the lowest frequency. You know that? Infrared has the highest wave, lowest frequency, longest wavelength. UV light, highest frequency, shortest wavelength. Correct? Okay. Yeah, ultraviolet. Yep. Okay, so up to this point, right, you should be having these questions in mind. Okay, if you are thinking, how come only transition metal exhibits color? Why? How come main group metal colorless? Why? Okay. Oh, why is there a color change when my ligand change? Why is there a color change when there's a redox reaction? Why? Okay. All right. So in this case, right, let's recap some of your year one topic. Do you still remember what are the different shapes of your d orbitals? All right, this one is learned in physics, right? Yeah, okay. Anyway, chemistry don't need this, but the relationship you must know, inversely proportional to the wavelength. Okay, so on page 16, we are trying to recap the different shapes of the d orbitals. Okay, so this one is in your syllabus, you must know how to draw. Okay, so the XYZ axis must be there. So you have a ds square y square. So ds square minus y square means that the loops are along x and y axis. dz square is the loops is along the z axis. Okay, then if you have your xy, xz, and yz, then the loops are in between the axes. Okay, so in the absence of ligands, meaning if the transition metal cation is in the gaseous state, no other interaction, then these d orbitals are degenerate. Do you still remember what is the meaning of degenerate? Huh? Yeah, they are of the same energy level. So even though these d orbitals, they lie along different axes, they have slightly different shape, they are of the same energy. Right? They are degenerate. Okay, but that's provided there's no ligands. Okay, so what happens if there are ligands? What's the significance of ligands? So can you read the next page? Can I give you like 5 minutes to read the next page? Then I'll go through the main points. Page 17. I have 5 minutes left. Okay, so more or less that. Yeah, so in this case, right, the gist is there is a repulsion experienced when your cation center interacts with the incoming ligands because both are electron rich. Okay, so ligands has lone pairs, therefore they are electron rich. There are electrons in the d orbitals, which can also repel the incoming lone pairs. Okay, so because of this repulsive force, the energy level of your d orbitals will be raised. So if you look at this particular diagram, right, appreciate that all of them will be raised in energy level, but to a different extent. Okay, simply because two of the orbitals have a head-on interaction, while the other three orbitals had a so-called side-on interaction. Okay, so it will result in a gap in the energy level between these two groups of d orbitals. So this energy gap is known as delta E, or you call it a crystal field splitting energy, okay, as given to you in the above. Crystal field splitting energy. Okay, and please take note, this delta E magnitude is affected by the nature or the strength of the approaching ligand, as well as the number of electrons in the d orbitals. Yeah, the two sets is because one is head-on interaction while the other one is side-on. Yeah, so therefore, because there's a repulsive force, that means you are disturbing it. You are making it unstable. Yeah, and the instability caused by the repulsion is different extents because of head-on and side-on interaction. Yeah. Okay, and this delta E is the one that will dictate what is the wavelength of the visible light range absorbed. And whatever that is left, right, or reflected back to you will be observed as a color. Okay, so is it logical for you to deduce that the number of electrons in the d orbitals affect? Why? Why the number of electrons in the d orbitals will affect delta E? Why? What do you think? What do you think? And the number of electrons in the d orbitals is related to oxidation number, right? So if your oxidation number is more positive, then there will be less electrons remaining in the d orbitals. So does it mean that there's more repulsion or less repulsion? More or less repulsion. Less electron in the d orbitals, higher oxidation number, but less electrons, right? So there will be less repulsion. So your delta E will be of a smaller magnitude, in other words. Okay. Now, the extent of repulsion also increases with your ligands. Okay, changes with your ligands. So your ligand, if your ligand is very willing to share the lone pair, or it forms a very strong dative covalent bond with your TM cation, then the repulsive force will be higher. Okay. So if you are forming a stronger bond, then the repulsion will be more significant. Okay, but it's not in your syllabus for you to deduce which ligand is a stronger ligand. It's not in your syllabus. So it's just for appreciation. When ligand change, delta E affected, therefore color changes. Okay, so we'll stop here for today. Right, the next time I see you, right, I'll go through the rest. Then most probably, right, I can go through the electrolytic tutorial also. So please check your answer soon. Okay, all right, that's all for today.